invitation. It's really nice to come here. I particularly like this workshop, by the way. So it's always a pleasure. So the talk I'm going to give, please do interrupt. It's a talk that, it's a topic that we're going to make some questions. I think it's a topic that we can all agree on a lot, but then it gets tricky on the interpretation bit. So I'm really happy to have discussion at any time. So feel free to interrupt. Before we begin, I guess I'm shamelessly going to use my speaker privilege because it was a measurement problem in QFT was mentioned, so a little bit of a shout out to two things. Something that I've done with grassroots of mine and our views on measurement theory in QFT, and also shout out on maybe Doreen may mention in her talk, but a paper preparation by Maria Papageorgiou and the inflation that will come soon. And I won't say much about this. This is advertisement if you want. All right, let's talk about gravity-induced entanglement. Now I'm going to talk mainly about what is in these papers by Thales. I call him Thales. He goes by Rick. Thales Rick Birch. That person here who couldn't come is a PhD student of mine, currently in the UK. But just so you know his face and who he is, you can recognize him and ask him questions too. All right, so what's the idea here? The idea is, all right, we've been doing our first experiments in gravity, if you want, or at least the first ones that we're doing in a way that reveals some information about what gravity looks like, not counting astronomical observations of the solar system. We're actually made a tabletop experiment. We have here the Cavendish experiment, and the question that we have here is, well, first of all, there's an interesting observation here. Obviously, we have models to describe the physics of matter, and matter interacts gravitationally. Matter with matter interacting gravitationally, and we know that matter behaves quantumly. So, what is the reflection of that? What is the effect that that has? The fact that matter is quantum, right? Interacting through gravity, can that somehow inform us about anything quantum about gravity? Right? So that is kind of the main motivation. So there's one thing that we know already from theory. We know that, well, the moment that something quantum couples with something classical, model is inconsistent. There's no consistent way of writing a phase-space picture, let alone either quantum or classical to begin with, that is at the same time contains observables that are dynamical functions that are not quantum, with fully quantized self-adjoint representations of those dynamical variables through a quantization map. So this is well known from theory. The fact that the hybrid models are inconsistent. In fact, you will find in those papers that Danny Turner, for example, writes explicitly, well, he makes claims about, well, that may mean that if quantum matter interacts gravitationally, there has to be something, either quantum theory is all wrong, but there has to be something quantum about gravity. But that's theory, right? So what we will learn, can we do a tabletop experiment, something like a Cavendish, maybe a more involved version of a Cavendish experiment, and learn something about perhaps the quantum nature of gravity. Okay, so what I'm going to talk about is this question here. Oh, by the way, I didn't mention, you will recognize some presentation mediocre slides. Those are mine 100%, and then you will see some slides that are better presented. Those are slides that I shamefully or shamelessly lifted from Thales that I presented to my students. You will recognize, you will see. You'll be able to tell which ones. Anyway, so the questions I'm gonna answer here is, okay, can the gravitational interaction entangle answer, or not answer, but focus on, can the gravitational interaction entangle two masses? What would that tell us? The answer to that question about the quantum nature of gravity. And again, if the answer is affirmative, then what? What do we learn by observing it? One thing is trying to model it, another one is observing it. What conclusions can we derive from that? Okay, you see what I mean, right? Anyway, so you see, this is an interesting plug. Let's talk a little bit about an introduction of something simpler than QFT or quantum gravity. So we know that fundamentally, all interactions, perhaps modulo gravity, right, are described, and we know the models are described in terms of quantum fields. However, oftentimes we don't use quantum field theory to describe scenarios. For example, take something very common in quantum information, that's the so-called J coupling. Two spins that couple through their magnetic moments. So that's a Hamiltonian that you get, obviously an effective Hamiltonian. There's no such thing as two spins, fundamentally speaking, or there's no such thing as J coupling, fundamentally speaking. We hope that these things are actually described microscopically in full detail by a fundamental model that involves quantum field theory. just not do that and instead do an effective model. This is an effective model. So I have this is the magnetic field sourced by a dipole that we can write. We know from classical field theory. Then of course we can write. You see, this is something that I did here. It's like, well, I go through a quantization map for the dynamical variables of the spins, say the position of the spin and the magnetic moment of the spin. I go through a quantization map, and then I write a self-adjoint operator, B, or BA and BB, that is a function of, or used to be a function of dynamical variables when we didn't have anything quantum, but now that I quantize matter, or I quantize the spins, right? It's a function of operators on the Hilbert space associated with the quantization of the degrees of freedom of the spin. Okay? Now, of course, I can write a Hamiltonian, that effective interaction Hamiltonian, and is used if you want to the nausea in quantum information or quantum information processing, of course. Of course, it's not relativistic, right? So this is no, we don't have any complications from having to describe the whole thing relativistically, but I could do a little trick here, which is considering the finite time, or considering if you want, something that is similar to the classical field theory description for the magnetic field, and here a retarded time that takes into account that the interaction takes some time to affect. So the potential, if you want, generated by this fellow takes a while to propagate to this fellow, and vice versa. And you can do that. This classical field theory, we can do that, and you end up with the Ricard potentials or other formulations of retarded potentials. So you could include that, and then you can have. Yeah.
H is an operator.
That's right. On the spins, on the Hilbert space of the spins.
Right.
Position of the spins and mu magnetic moment of the spins.
On the Schrödinger or Heisenberg space?
I'm doing Heisenberg picture.
On the Heisenberg.
Yeah. Doesn't matter. I could do either. I'm just saying one could be interaction picture to you. It's not relevant for the discussion. Right. But then, of course, we can wonder if this is proof that the field is quantum. Let's do observation. I'm not going to make any claims, but let's observe a difference between two models here. So here we can give operator valued fields if you want. So this is the magnetic field, and you can tell us it's got hats. It's certainly an operator valued function. It's function of space-time, time and position. And I can make it relativistic. I can include the relativistic potentials if you want. Retarded potential, I take into account the finite nature of the speed of light. And these are, I would claim, and we will talk more about that. We will talk more about that, because this claim is not an absolute claim. It's kind of interpretation, and we will talk about that. I would claim that these are not quantum fields in the sense that I don't have dynamical variables associated with B, with the field B, that I quantize and in a Hilbert space that's associated to the field. My Hilbert spaces here are just belonging to the space, if you want. We can talk about it whether it is equivalent or not yet, right?
So these expressions are not solutions to some equation, the notion for the B, these are definitions.
In the sense that it's an effective model, yes, exactly. I gave it the magnetic field generated. It's not coming from the dynamics of putting the spins together and interacting with the field. It's a prescribed model, 100%. And my question is, well, I have an experiment that is described by this prescribed model. It doesn't come from foundational principles. It's prescribed. It comes from observation. And this model is predicting the outcome of an experiment. I would wonder whether this could be used for proof. This is just to introduce the topic. We could use for proof that the field is quantum because it's, in a way I have aspirator value. Yeah.
But this can be in quantum superposition.
The field can be in quantum superposition depending on what is meant by that. Right? You see the Hilbert space here. It's the
in a
space.
generic situation, does the field have the same value as last?
Well, no. You see, we have here the fields are entirely determined by the quantum force. This is, I'm giving you an operator value distribution that is well defined at every point in space-time as an operator, and it's an operator of the Hilbert space of the spins.
So it can have negative values, and in a generic situation, the state is a superposition of these negative values.
I agree, yes.
So why wouldn't everybody call this a quantum?
Well, I don't need to go through the process of second. I will hopefully get more into that. But I didn't have the quantization procedure from the phase space of the field because I don't have a phase space of the field. It's an effective model. I just gave you a contact interaction that is mediated by a retarded potential. And the Hilbert space here belongs to matter, not the field. It belongs to the spins, so the degrees of freedom are spins degrees of freedom.
Exactly, with words. This is something defined everywhere in space-time, which can be in different configuration, different superposition. So what this specific simplification to the dynamic will take doesn't take away the fact that it's in a quantum space. It can be in a quantum space.
So my point would be the following, right? Like whether we can claim that, for example, a J coupling between two spins is enough to say, oh yeah, no, the electromagnetic field is quantum or not. So I mean, if I have an experiment in a lab that I do J coupling for that experiment, would it be enough to say that the magnetic field is quantum, for example? That would be the question I would be asking.
If there is a field, yes. If you introduce a field, that field is quantum.
But there's no local degrees of freedom for that field. That's my point. Maybe let's go one more step.
This is worse.
I'm gonna make it more concise. What I mean. Okay, let's see. Let's go to QFT. Let's do it with a scalar. Let's quantize a classical field theory. I have now degrees of freedom of the field, so meaning that I have dynamical function, I have phase space, and I can define locally the degrees of freedom that the field has. It's infinitely many degrees of freedom, one at each point of space. We go through the quantization plan. So what I want to identify is what is quantum about quantizing a field. So I have a field theory, a scalar field theory, say. My question would be, what is quantum? So now I'm going to make from a classical field theory a quantum field theory. I'm going to go through a quantization map. In other words, what do I have when h bar is 0 for the field? And what do I have when h bar is a finite value? Let me put it like that. Let's identify what the h bars could be in the theory. Now, certainly, when I implement commutation relations, when I map my Poisson bracket to an I commutator, right, I h bar commutator, certainly there's an h bar in here. This thing is, I would say, it's a quantum thing. The commutator of the field at two different points in space-time is a quantum field. There's certainly an h bar in there. If I make h bar 0, that is 0. Yeah, so I'm talking now about a free field. So yeah, that's important. But it's whether the quantumness lives in matter or lives in the field, for me, makes a difference. And maybe that's what we can discuss later on. So for now, in this case in particular, think of a field as, you see, in the other one, the field is not mediated. In the effective model that I give, the field is no mediator of the interaction. It's an effective interaction that I give. There's no such thing as suddenly information goes from the spins, it's dumped into the field transmits that information, and the information gets to the other spin. In the model that I gave, it's just a plain Hamiltonian that couples the two by contact interaction. So in that sense, there's no information transmission through the field, because the field doesn't have local degrees of freedom to deposit quantum information. But hopefully it will be clear as we continue, and I'm looking forward to the discussion on this in particular.
And the B field you define is actually just on the Hilbert space of the particle.
Precisely. Yeah. There's no other Hilbert space there. That's what I mean, no local degrees of freedom. Yeah. All right, so there's now I'm considering a fully fledged dynamical, very easy, a scalar field theory, right? But fully fledged dynamicals got local degrees of freedom and quantizing it, and certainly I don't think many people would argue that the commutator is not a quantum thing. Well, there's an h bar. If I make h bar equals 0, that thing for a free field would go to 0. Now, I wanted to focus on two objects that are going to become relevant for the talk, which are the Weinmann function and the Feynman propagator. Now, the Weinmann function, I can write, the Feynman propagator, I can write as its imaginary part plus its real part, antisymmetric part, symmetric part. The imaginary part of the Weinmann function is the commutator, of course, the expectation of the commutator. And there's another term, this term is the Hahnemann distribution. And we have similarly, for the Feynman propagator, we get two terms, the imaginary part and the real part. The imaginary part of the Feynman propagator is actually what we call the radiation green function, which is the retarded propagating function plus the advanced one. Yeah? The same thing that you would get if you solve classical field theory for a scalar field, the wave equation, the green function for the wave equation. And this H as well, which is, right? Both the commutator and the green function, the radiation green function, if you want the retarded propagator plus the advanced one, both are state independent. They are not dependent on this omega, right? They're completely state configuration independent, if you want. Like those things don't depend on this. H does. In particular, for example, you can have a Hadamard space, and then you can call maybe your Minkowski space, and you can call it the vacuum. And this thing has some value, right? That this doesn't exist. Classically, for example, the vacuum would be this. expectation of a classical field in the vacuum, or the ground state if you want, the theory is 0, whereas here we have something else, right? So I'm going to declare, and please, if you disagree, let me know. I'm going to agree that this is E state-dependent on quantum, as we discussed, is the commutator. Certainly an H bar in there. When I make H bar going to 0, this will not vanish. The state-independent part here, I call it classical. It's certainly the green function associated with the propagation of, if you want, information in the classical field as well. Doesn't have an H bar. If I were to make H bar going to 0, that doesn't go to 0. Now you can discuss whether H or not has an H bar. I'm going to argue, well, certainly. This is the state-dependent terms. For example, that would be the symmetric part of the vacuum expectation. You have a vacuum field in general. To prepare a state, you can prepare states that are very quantum, like superpositions, for example, of states of the field, if you want, right? Things that live in the Hilbert space that don't have a classical analog. This H in general is quantum. This will, in general, is very dependent on the fact that the field is quantized. We went through a process that based on H bar. And if you disagree, please let me know. I did.
You're saying that you want to hold in classical quantum. One can't disagree with names.
Fair enough, but there are loads of
If
things.
a meaning to these names, then maybe we disagree.
Okay, the meaning is, so when I make H bar going to 0, this is going to go to 0. Say for a vacuum. Say that I am thinking of Minkowski spacetime, scalar field theory free, and I consider the ground state of the theory, both classically and quantumly. I obtain the classical theory by taking H bar going to 0. This disappears, this remains, and this is the propagator that I get for the theory. That's why I call it classical. When I make H bar go to 0, for the field quantization sector, this is something, except for this, which is the classical propagation. That's what I mean by the difference. Now, after this, so let's keep that in mind. I think I want you to remember this. Can we, let's make the effort to remember this. I know some of you will, but just in case, there are slides that are more important than others, this one is important. Let's remember that for later on. Let's talk about one particular case of gravity-induced entanglement experiment, the DLG experiment, beautiful experiment. And in fact, an experiment that very likely will be able to be done in the next decades, in my opinion. So this was originally proposed by Eduardo and collaborators. And then there's a lot of theoretical work on the side of Eduardo and Martinez. Many people have worked on that. Carlos has published a lot of papers on that, with more insight on these kinds of experiments, and many other people. What is this experiment? So let me just describe it. In the original, I'm going to go with the original. We're going to go with the original before getting into nuance. The original description of the experiment by Bose and collaborators. So we have here two masses that I can place in a superposition of two trajectories. Okay? So we have the, if you want, the center of mass degree of freedom for the system 1, the center of mass degree of freedom for system 2. Those are quantum. As we know, quantum mechanics works really well to describe those systems, so the position of those systems, rather, the center of mass degree of freedom of those systems. And we prepare, say, a superposition of system number 1 going into trajectories, and same for system number 2. Of course, there are correlates. You can tell here this is a separate product thing. There's no correlation between them, but each of them are in a superposition of going left side or right side, left side or right side. Yep. So the question that we have that this paper addresses is the following. Say that they're interacting, let me simplify, with under a Newtonian potential. So you can tell under a Newtonian potential, now there's a having here, and if you just naively, not naively, meaning, it's not naive at all, if you just do time evolution under that potential, it's not nice to do it, you of course get different phases depending on what path you're going, obviously, because some of them are closer than others, right? And turns out that at the end, the final state here is not separable. The two masses have become entangled under the Newtonian interaction. Okay? Now, let's go through a nuanced arguments to find. So again, this is I'm going to write the arguments in a way that hopefully mimics a little bit the original discussions that happened, and then we'll get to the nuance. All right. So what can we claim if we observe entanglement? It would be really cool, by the way. First of all, gravity-induced entanglement experiment would be extremely cute. It's really cool. It's, as we will mention later, you know, we have general relativity. General relativity fails to be satisfactory internally. We know general relativity is wrong, or either everything else we know, but general relativity predicts its own demise. And yet, we haven't found any experimental observation that goes beyond semi-classical gravity. But this could be the first one, which is kind of nice. If somebody can do a gravity-induced entanglement experiment. Anyway, how far can we take our claims if somebody observes? This is what I want to discuss. How far can we take our claims if somebody does this experiment and observes entanglement? Okay. So this is a bit of a reasoning, and I'm paraphrasing, so my apologies if I'm not representing this with enough justice, to do justice to that paper. But the argument goes a little bit like that. Well, LOCC cannot increase entanglement between quantum systems. Local operation and classical communication. Thus, if the masses interact only gravitationally and get entangled, then the gravitational field which mediates the interaction is going somehow beyond the classical communication. You have to exchange quantum information in order to get entangled. So the fields cannot be classical since it's established as a quantum channel, something that, you know, genuinely quantum channel. What quantum information would say is a genuinely quantum channel. You have a separable state and you end up with an entanglement. That was the first time. Well, this is way more refined analytics, but let's begin with it. Well, something even more powerful, right? What Marletto and Vedral published, which is extremely beautiful, is that they actually prove that if a third system locally mediates an interaction between systems 1 and 2, say a system 3, in this case would be a gravitational field, right? Then the intermediary system has to be quantum. They give compelling arguments, compelling theorems, that should be the case. So, conclusions. So you see, with this reasoning, one should conclude, perhaps, that if you observe entanglement in a gravity-induced entanglement experiment, then this is proof that gravity has to be quantum, because, you know, there's no intermediary system that is not quantum that can do it. That goes along the lines of those papers that I mentioned at the beginning on the consistency in coupling quantum and classical systems. So, a little bit of nuance about assumptions. But is gravity an intermediary system? Am I making a I don't think anybody in the room, or maybe yes, but I don't know, thinks that there's no such thing as a gravitational field with dynamical degrees of freedom. But from the point of view of, let's be skeptical about what the experiment assumes and what the experiment proves, are we making a hidden assumption when we do that? And then an answer to this would be, well, if you don't assume that the gravitational field has local degrees of freedom, that you're dumping information there and the information propagates, then you have a problem. You have a non-local interaction, like a contact interaction, like I showed you with the magnetic field, right? And that may allow for superluminal signaling on things that are not okay from even the axiomatic point of view, if you want, depending on how much you believe in that, right? At those scales, I don't think anybody would disagree, but you don't want a theory that violates relativity at those scales. At scales of a tabletop low-energy experiment of gravity-induced entanglement. Now, the idea would be, okay, mass 1 couples to the field, and then the field carries quantum information to mass 2. Otherwise, we would have non-local, some sort of action at a distance. Well, okay, let's discuss a little bit these two notions before going to the... So far, so good? Okay. Now, the notions of locality, let me just be a little explicit about that. I have to apologize, I was aware of the paper that you put out on this recently only. I found that I haven't had time to read the last paper that you wrote on this topic.
I don't think it's relevant.
Fair enough. I just saw the title and said, okay, maybe. I'm going to talk about two notions of locality. One is event locality. What are we calling event locality? Well, let me define it in a space-time framework. It's actually more powerful. Let me define a space-time framework. Operations happen at events in space-time. So I postulate here there's a notion of space-time. And do not affect other events which are causally disconnected from them. So we have some causal structure between events, which is space-time, which is the set of events. And we have a notion of, well, causal structure. A and B cannot be causally related unless some conditions are satisfied. If you are doing special relativity, for example, there will be relativistic causality. Okay? If you're doing something else, it will be something else. But we assume there's a structure, there's a causal structure, and a notion of event locality based on that. Now, we also have a different notion This event locality notion is fundamental. It's fundamental at the level of foundations. It's something that our experiments, our observation of the world seem to be telling us is true. That we cannot influence events that are really far away from us unless we wait enough time. There's another notion, which is what I call here called system locality. It's specific to quantum mechanics. And basically, let me summarize a lot. Operations that independently affect the quantum system must be of this one. Maybe this is a way, assuming that you say, okay, I'm doing operations in a joint system A, B, and I'm doing an operation that affects A but doesn't affect B whatsoever, I better be able to write this as UA tensor identity on B as an operator. I've got a unitary here as an operator that acts on the total system. It has to be some local action on A and some local action on B. Now, these two things are different. You see, one is fundamental, the other one is a specific implementation of a notion of locality in quantum mechanics. In a way, it's an operational notion. It's a way to make it. If I didn't tell you anything else, it's a way to make it to make explicit that in quantum mechanics, operationally speaking. There is one framework. I don't know if I have that. Yeah. There is one framework though, with the two notions are related, and we probably know what framework that is. That's what we call QFT. In QFT, we have a microcausality action, some others, that imposes the relationship between the two. Basically, we're saying when we build a QFT, most of the time, we're saying axiomatically that the notion of event locality is intrinsically related to system locality. Now, if we want to prove that something may be described as something that is something like a QFT that has local degrees of freedom, it may or may not be allowed to make this link from the beginning. And that's one of the things I want to discuss. I'm going to give you two different descriptions for the BMD experiment. Two models, if you want, two mathematical models. One more fundamental than the other. In fact, one of them is not fundamental at all. One of them is an effective model. Of course, based on some assumptions that hopefully are reasonable, we will discuss. I will call that one quantum control field. And the other one is QFT. I'm going to give you a QFT description for gravity, where you can get the BMD experiment. Luckily, this is weak gravity. We are in weak gravity regime, so we know how to quantize weak gravitational fields. That's good. We can build a full quantum model. So, let me give you a little bit of hand-waving motivation and introduction of the results of the prediction, and then we'll analyze a little bit from the slide that I told you to remember later. All right. So, first, both cases we're going to consider. We're going to try to describe the experiment with weak gravity, right? So basically, we say, well, our boundary is Minkowski plus some small perturbation because those masses are not huge. All right, nice. But this is a classical theory. I can solve the equations of motion. No explicit case has been picked throughout this talk. Okay? I'm going to have the equations of motion for the metric perturbation, and I can write those equations of motion in terms of a green function that is sourced by the extraordinary density of the particle. Now, if it was one particle, two particles that were not in a superposition, everything is classical here. This is uncontroversial. This is classical field theory, so very uncontroversial. Okay? And that's the radiation green function, the same one that I talked about, the delta. Well, there are indices here, but we'll see. I'm going to actually show you. So then we couple, again, here is what would happen if we couple a small mass to the gravitational field. So the stationary density is given by some point-like mass trajectory, everything classical, no hats. And again, we have a model that is uncontroversial. It's classical field theory. Well, I don't know if uncontroversial is the word, because you can argue, oh, but is there back reaction? And if it's no back reaction, then it's causal. And there are many issues already with classical theory that I'm not getting into here. At least it's uncontroversial at the level of leading order corrections. All right. But this is not what we have. Now we have something else. And this is what makes the experiment interesting, right? No. You do have, these are quantum variables now. These trajectories are hats. There's a hyperspace representation for the observables of the particles that are moving. So you cannot do this model. It doesn't work anymore. We know that. Inconsistency. You cannot couple classical things to quantum. But what I can do is I can make up an effective model, same way that I did with the JJ coupling, and wonder whether, if the predictions of that model are good enough to predict the experiment, whether the experiment can or not be proved of quantum gravity, or to what level it can be proved. So let me give you a naive version to model this. I can call it naive because this is what we did. So I'm going to say this is a prescription of an effective model that the interaction Hamiltonian between the two masses is going to be the classical gravitational field generated by, of course, full relativistic description here. Huh? This is the potential that would come out of the full relativistic description. I will write it here in a second. And multiplied by the projector associated with particular choice of the projector. So basically, I'm assigning the classical field phi P1, P2 to the configuration P1, P2 of the masses. So I have four possible configurations, right? The mass goes through the left, and through the left, through the left, and through the right, and through the right. And all the combinations you can take. And I add one term per configuration. So this is a very nice, if you want, you can call it an incoherent superposition of the interactions. Okay? Very nice. Configuration of the paths associated with the potential, classical potential at each path. And you can do calculations with that. And in fact, when you see the delta there, delta is the radiation wave function. In fact, you get that the results that you get are a function of combinations of the possible paths with the classical, if you want, ring function. That is the delta that we have here. And of course, this is nice in the sense that it does recover. So if you go to the non-relativistic limit, it's easier in the paper to see that this is the Newtonian potential that Bose used, the model that he used. This is just a relativistic, classical field theory inspired relativistic description of the system. So okay, there's no classical description for the experiment. That is uncontroversial. But I gave you a very naive description where I associate the classical gravitational field per configuration of the particles. Now, of course, if the Newtonian potential gives entanglement, this one gives entanglement too, right? So as this evolution, the system of two masses evolves through an entanglement. I just wrote the result here. It's going to be prime. This is negativity. This is a measure of entanglement. In fact, faithful measure of entanglement for the cases that we're considering. Anyway, this measure of entanglement basically tells you that a leading order in the gravitational constant, the two masses get entangled. Okay? And they get entangled with this delta. So we might the radiation green function. Okay? Well, of course, there's no components here of anything like Feynman propagators, anything like that, because the field was never quantized in this description. I just naively associated the classical field with its configuration. So there's no room for Feynman functions, and there's no room for the real part of the Feynman propagator. There's no room for H bars in the field sector. Okay. Now, this is what I want to say. So, and I understand that this is not trivial thing because, well, let's see. This evolution does establish a quantum channel between the masses, it gets them entangled. However, the field has no local, I should say, quantum degrees of freedom, in the sense that the field is fixed, not dynamical, is what you said first. There's no dynamics that is even back reacting from the field and the particles in this model. It's an effective model. Okay. And certainly not quantized for the field part. So finding entanglement on the masses with gravitational interaction, I would say, does not mean that gravity has local quantum degrees of freedom. Because, well, I give you a model where there's no such thing. And you do have entanglement. You don't need it to have quantum degrees of freedom. I will qualify this statement. Maybe it's too strong as stated. The interaction is certainly not system local. It's a contact interaction, obviously. It's like the JJ coupling that I described before. It puts the operators of particle 1 in contact, right, as a sum of tensor products, if you want, not just a tensor product. It's not system local. However, though, for the regimes that we analyze in it, it's even local. It's relativistically local. It comes from a fully relativistic description of each of the terms. And again, in the regimes that this experiment is done, it's fully system local. So it's not violating event locality. It is violating system locality, but not event locality. Now, I'm not saying this model is good. I'm not saying this model is real. It is a model where the field has no dynamics. Okay, that's all I'm saying. Okay, so why? Why do I do that? Well, an interaction established in a quantum channel does not mean that it's mediated by a quantum system. That's what I would say. Maybe you have extra assumptions that would imply that, but just having the fact that you established a quantum channel doesn't mean that it can entangle. Doesn't mean that has to be mediated by a quantum system. Can still be event local at the same time, even if it's not, event local, I said, even if it's not system local. All right, let's do another model, better one. This one I actually, with bet money rather than the one that I presented before. I'm gonna consider linearized quantum gravity. So I have now a hat on the H mu. I go through the quantization map for the linear perturbation to the metric. So I have degrees of freedom of gravity. I have a dynamics for gravity. I have a phase space for gravity. And it evolves coupled to the masses. Now we can do exactly the same thing. What we have now, what I did now, is I coupled this interaction Hamiltonian is coupling the stress energy density of the masses. There should be a hat in the T, which I didn't put, of course. But this different kind of hat. You see, H is a hat of an operator, so an operator that lives or acts on the Hilbert space associated with the field degrees of freedom. Whereas T is an operator on the matter degrees of freedom. Okay? Now, nice, this is a linear interaction theory, so I don't get into the complications that you would get otherwise with gravity. Now, of course, I would argue this is a linear theory, but no matter your quantum gravity, I would argue that one should expect that this would be the weak limit of quantum gravity, whatever that is. All right, so same setup as before, but now gravity is locally quantized, and we need initial conditions as well for the gravitational field. Let's say that we're in the vacuum, in the Minkowski vacuum, background space-time is flat, our perturbation. We're in the Minkowski vacuum for the gravitational field. Let's see what happens when I do the same thing. Well, when you do the same thing, you also find entanglement. Now, fun part, you find less entanglement in some cases, and why? You see the difference, there's a minus, maybe I should, yeah, here's the detail of the calculation. Anyway, you see, I don't know if you remember, I will show you both, the prediction with the previous model and this one. There's a minus L in this one. That's an oyster, that's bad. That is subtracted from the entanglement. Where does that come from? Well, that comes from the fact that when the gravitational field is quantum, the degrees of freedom of matter get entangled with the field itself. There's some decoherence, if you want, induced by the fact that some of the information, not all the information from A reaches B. There's some information that gets deposited in the field and lives in the field forever. So there is decoherence. In the previous model, the state of the masses remains pure. This is a unitary interaction between two masses. Here is not. Here, the two masses interact with an intermediary system, the gravitational field, or the perturbation of the metric, if you want. And they get entangled individually with the perturbation with the gravitational field. Okay, so that's where the L comes from. That's the vacuum excitation probability, if you want, of the masses. If you want to call it that. The equivalent in atomic physics would be a vacuum excitation probability, spontaneously from vacuum fluctuations. That's a big difference. There's also other differences. As you see, we have here this G with many indices is the Feynman propagator associated with the gravitational perturbation of the field. The imaginary part being the radiation green function and the Hadamard part. Okay? So you see the difference. The main difference is two things. You have the L term there subtracted, and what was the deltas now is the G's. What was the radiation green function is now the Feynman propagator in this calculation. This is fully dynamical for the field as well. The field evolves in time in that sense. So I've turned on all the dynamics. The field has dynamics, the masses have dynamics. This is not an effective model. Well, I mean, it is, right? Because we don't know what quantum gravity really is. But in the context of linearized gravity, linearized quantum gravity is a full model. It's a QFT for the field. So of course, this also predicts, of course, that the masses will get entangled. And now in the way that everybody thinks of, right? Because you don't have mass 1. Mass 1 gets entangled with the field, and there's quantum information deposited along the trajectory of mass 1, and that information gets propagated by the field living in the field and gets to mass 2. So it's an intermediary field transmitting information between the two. Okay, so let's compare the two, and then let's go back to that slide that I mentioned. The model that I call quantum control. So the reason I call it quantum control is because the quantumness of gravity here comes from the matter degrees of freedom. It comes from the fact that the arc of the mass had a hat, if you want. Whereas here is a quantization process on the field, quantization map. Now, in both cases, as I said, the difference is Feynman propagator versus radiation propagator, green function, and the local ones. Oh, there's a big difference though. It's not the only difference. These things will produce different numbers, obviously. Like if you predict how much entanglement is going to be different in the two models. both predict entanglement, except for one regime, right? If the masses are space-like separated, for example, the quantum model will predict entanglement. There is entanglement in the ground state already. Strictly the kind of entanglement. And the two masses harvest that entanglement that exists in the field. This is why in relativistic quantum information that's typically called entanglement harvesting. Whereas in the quantum control classical gravity, there's no quantum degrees of freedom from the gravitational field. The detectors can never, because it's fully relativistic, can never get entangled by interacting with their spaces in the quantum control model. Okay. Now, let me just show you first a perturbative argument and then a non-perturbative one about what's going on. I have here two cases. Now, those are the density matrix of the two masses in the basis. Doesn't matter as much what basis I picked, but look at them. Right? You have the local noises. You have look at the terms in the anti-diagonal as the one responsible for the entanglement at the end. And the correction to the first term here is higher order, and the correction here is higher order. I believe it didn't write them here. But let's look at the difference between the two. This is the state of the masses. You know, they're regular masses, non-relativistic. It's not a field theory for the masses. It's another thing that one can ask about. Those masses are quantum mechanical, and they couple through the gravitational field. In the case that we have a proper quantum field, this H is quantized as a hat local degrees of freedom. I got that density matrix. In the case that we use the model, the ad hoc model, where I associated a classical field to each configuration of the masses, I'll obtain the second model over there. And we can compare and see when they become the same. Because in some regimes, they're going to be the same. That's the nice thing. This thing, we know there's a common limit, right? The Newtonian limit is common to both. So of course, there are regimes that they predict the same. Well, recall that thing that I told you about. The Wyman function has a quantum component. The Feynman propagator has a what I call classical component, the radiation ring function, and a quantum component. What happens if I make h bar going to 0 in the quantization of the field? What happens if I get the fully quantum model and I say, but for the field sector, I'm going to make h bar equals 0 for the field sector. What happens then? Well, what happens is, of course, that you lose all that. And what you're left with, the Wyman function cancels completely for the vacuum. So the L terms cancel completely. And the M terms, become the same. So when I cross out h bar from the quantization sector of the field, the two models predict the same. That was a perturbative argument, but we can actually do a integral.
What was the 4-4 element of that? What's the 4-4 element of the matrix?
It's higher order in G, so I don't even consider this as completely in order in G. This one is higher order. This one is higher order. It shouldn't even be there. Okay, so yeah, basically M is the right order. M squared is higher order. All right, so we can do it. We can write the path integral for these two theories, right? You have the full model with quantum degrees of freedom. You have linearized gravity, and you have the two masses, right? And you can say, okay, how do I obtain the QC model? Well, what you do is you remove the dynamics from the quantum field theory, and also map the Feynman propagator to the radiation ring function, and indeed, you get the model that predicts the same interaction Hamiltonian. Right. So the argument that they become the same when you cross out h bar is true non-perturbatively, not just perturbatively. Okay, so back to this. We have a model that, how am I doing time-wise, by the way?
We're getting close to that.
Yeah, I think two. Yeah, because I want to get to it. Okay, I hope that this is clear. I'm going to skip this. All right, so one thing that I would say is that the current proposal, we're going to talk about the experiment in general. The current proposals focus on regimes, and it makes sense. Those are the first one that they can do, where there's nothing weird going on with the masses, so the masses are just split in two and going constant paths, and they're within causal quantum. Within those regimes, you cannot really distinguish the predictions of the two models. That's what I'm saying. There's no distinction. They're numerically different, but the amount of accuracy in measuring entanglement that you would need is crazy in order to distinguish the two. So you will not be able, the experiment as proposed, will not be able to distinguish the two models that I talked about. Now, this is now the opinion part. That's what I want to do in the last one. I I gave you some things, right? That are, if you believe, if you trust my math, or Thales's math, which is probably better, then now it's time that you would agree with everything. But let's try to extract conclusions. Yeah. That's what I always say. Like, somebody does the experiment. Would you give them the Nobel Prize? Well, I mean, so what? Why would you? What has been proved, right? If you do the experiment. So I would. This is opinion. So my opinion. Certainly, the experiment is great. It does several things. It proves it's an experimental proof that semi-classical gravity fails to describe the experiment. Semi-classical gravity, where you just put expectation values until you knew, does not give that prediction. Cannot entangle anything. In fact, it disproves a lot of stochastic theories. There's a lot of local stochastic theories that will be disproven by this experiment for gravity. Not all of them, but a good chunk of them. That, to be completely fair, nobody trusted for other reasons. Many of them, like the Milburn, well, whatever, we can discuss it. But yeah, it definitely experimental proof. Every argument against all those things was theoretical so far. So it's very important in physics that we have an experiment that disproves that. No questions asked. Maybe that alone deserves the Nobel Prize. I don't know. It also proves that gravity can set up a quantum channel between masses. Now, you tell this to the quantum information community, they say, oh, that's a sign of non-classicality indeed. If gravity can establish a quantum channel, it must be quantum. So these things, I agree. Now, where I disagree, or I would argue that the experiment does not prove the existence of local quantum degrees of freedom for gravity. So I gave a model where there's no local degrees of freedom of gravity. In fact, it comes from making h bar equal to 0 in the quantization sector of the field. That reproduces entanglement. And it's relativistic, so it's still local in the relativistic sense. It doesn't violate signaling of any kind. I also would argue, and again, this is very, one would need to talk about what you mean by this. And I've talked with this, I think like Czesław, for example, Czesław Brunner has a definition for this that, yeah, I would agree it's true, but let me tell you what I mean by this. I would not say that it proves that there's a quantum superposition of spacetimes. And the reason I would say that is because, well, there's no Hilbert space for spacetime. It's matter Hilbert space. Now, I get the arguments. Yeah, you cannot define the field at a point in spacetime. In that sense, there's a superposition in some Hilbert space for it. But it's certainly not a superposition in a Hilbert space that you associate with spacetime directly. At least there's a model that does it, right? That without having to assume that. Okay, so maybe just the last slide, for sure. I would argue that the detection of entanglement itself is agnostic. It's not agnostic to many things, but certainly agnostic to the existence of local quantum degrees of freedom in gravity. Give you a model, a contact model that reproduces it. It's like JJ coupling in a way. Now, unless one assumes some extra connection between event locality and system locality, because certainly the model that I proposed is not local in the quantum sense. There's contact interactions, right? But I would argue that if you assume that, you're assuming already a framework like QFT that maybe it's like what you started, that you set out to prove in the first hand, so in the first point, right? So maybe it's not a good assumption to assume that the two are linked from scratch, right? Now, there are many smoking guns. I wrote this one, but there are others. There are regimes. For example, Wald and Flaminia and Esteban, I don't remember all the authors, but they talk about a setup where you have one-way signaling only. And that setup will distinguish the two really well. The predictions in that one, you see, when you are deep into the time-like area of the experiment, so very long lasting experiments, the two models coincide. And they even go to the Newtonian limit in the limit. But if you go to any regime outside of that, well, certainly you'll be able to distinguish if it's a theory with local degrees of freedom. You can do something fancy. You can move the masses, make them move and back react strongly with the field, make them so that the self-interaction with the masses is huge as compared, even normalized, huge as compared to the interaction between the two. And that will reveal some quantum nature of the gravitational field as well. Or, well, yeah, finding entanglement in space-time separation between the masses, that would be huge, but also practical, of course, because the amount of entanglement is tiny in those cases, right? But you need, like Walt pointed out, and same as the conclusion we get here, you will need very short-time regimes, which is not what the experiment right now is saying. Very short-time regimes to really claim, in my opinion, that is an uncontroversial proof of the quantum nature of gravity. I think that's pretty much it. I would love discussion.
Okay, let's start with Adam.
Yeah, thanks. Topic is interesting. I'm convinced of the point that the experiment might not establish that they agree in these limits, but I'm curious about the analogy that you Okay, so there you have a point where, look, we have this contact, or like this sort of non-local effective description, but what's underlying it is actually, we know in that case, is actually a quantum
In that case, we know it.
description. So is there a good argument, theoretically, that we shouldn't expect something like that to underlie gravity, other than just we can't be sure?
I'm a believer in quantum gravity, for sure. So that's a reasonability. I'm getting the spectrum route here, right? In the skeptic route, if you want. I agree with you. We've seen it with this, right? But there are so many subtleties, like, for example, gauge theories in general, right? Gravity is a very difficult gauge theory, to the point that some people even discuss whether it's a gauge theory or something else. When we have gauge theories, finding at the same time observables that are gauge independent and local, I don't know, maybe tomorrow people will discuss all those things. Wilson. But you see, when you get gauge theory, so the reasoning that works for electromagnetism, because we know we have a fully quantum description for this already, can be an argument towards we should expect the same. But I think that with the experiment, we want to set out to prove it, which is different, right? It's very reasonable. Don't interpret my talk as I don't believe gravity is, that I believe that gravity can be described with an effective theory and is emergent of some kind. But it could be, that's what I mean.
Carl?
I'm not convinced.
I know.
Let me make just a very small general point and then tell you specifically, technically, where it is. The general point is that, I don't know what you're arguing about. You never prove a very general point in words with an experiment. Even any experiment that you want, and I can turn up words to not derive from that general theory. You don't prove a theory. It's not even clear whether you disprove a theory. Maybe here there's a case in which you could do it. So I'm not sure exactly what you're saying. What you seem to be saying here is, look, I have a model which you agree that it sort of disagrees with other things we believe are credible about the world. Namely, there is a gravitational field which agrees with it. And so far, this was the thing. I mean, both and other papers started by saying this experiment by itself doesn't prove anything. It said very clearly, unless you assume Lorentz invariance. And it seems to be you to be saying, well, he should have said not unless I assume Lorentz invariant, but rather unless I assume there is a gravitational field. Okay, it's a minor right. It should have been a little bit more precise, but doesn't change the situation. But let me go to the technical point, because the technical point is that you say, can you go to the penultimate slide? You say that the
Here?
the very
Sorry.
yeah.
This one, probably. Oh, the previous one.
Yes. You say that the Hilbert space is a Hilbert space of matter. Now, technically, I don't see how this can be the case, because the specific case, we have two particles. Okay, you can think and simplify this before. The Hilbert space of two particles, we know what it is L2 of R tensor L2 of R, say one dimension. But you can't do a model within this Hilbert space. This can be shown in the Schrödinger, and there's a physical version of that. This can be shown in the Schrödinger picture or the other picture. Let me know the Schrödinger picture is easier. Okay? If you use the Schrödinger picture, you can always, the Hilbert space is the information that we can get at some time from which we can derive the future. Now, if I know the quantum state of the particles in your model at some time, quantum state, I cannot predict the future, obviously, because the future depends, the movement of one particle depends how the other particle was in the past. So the information at some time is much more than L2 of R plus L2 of R. Okay? So the actual Hilbert space is much, much bigger. Okay. Now Feynman and Gill in the past took quantum electrodynamics and reformulated.
Absorber theory.
Basically, they did what you do. Okay? It's just a Feynman-Gill version of the same thing, in which they say, well, they're the particles, and the field at some point, assuming no incoming waves, can be uniquely determined by the past history of the particle. Okay? So it's your model. But they never said this is not a quantum field theory, it's a reformulation of quantum field theory. So let me be precise here. If at some point, I want to know, at some time slice, I want to know what happened
independent from the particle at that time. And that's what we mean by quantum field theory. So I think that your math is good, is correct, but your rhetoric, it's not, because you're just reformulating a corner of quantum field theory and saying, well, if I don't have incoming waves, that's what you're saying, I still have the effect. Yes, we'll agree about that. But I would still, and in particular, and that is when you say that it does not imply that the gravitation of field forget space-time implies counter-intuitive gravitational field. If I want to think that the gravitational field is space-time, the same thing, but I might not want to do that. In your theory, there is a field which can be measured. In fact, the measurement itself is a measurement of the field. And this field is in superposition. Namely, if I do various repetitions of the same experimental situation, I can get sometimes one and sometimes the other, and sometimes I can measure something which depends on the interference between the two. This is what. So the fact that you say I can reformulate in this way and hold on to the expression is classical, is classical, is classical.
I never said it's classical.
Well, it's not quantum, it's not quantum, it's not quantum. I think it's just creating a huge confusion in the field and a big mess for no reason whatsoever. That's my opinion. There's nothing wrong with the equations, but in the words you attach to it.
Well, so that maybe answer it step by step. So the thing is that I agree with a lot of what you said. There's some things that I don't, right? This is not an absorber theory formulation or Feynman-Wheeler formulation. In fact, the two predictions are different. So the two models that I give are not equivalent. They do have the same limit. One is one in which I have associated what would be the value of the classical field per configuration, and the other one is a fully dynamical QFT theory, right? So I'm not doing. I would agree that if somebody, for gravity, as far as I know, that doesn't exist, right? But if somebody were to do a Feynman-Wheeler description of quantized gravitational field, that is equivalent 100%. This is not. So it's very important. The model that I present is not a Feynman-Wheeler description.
Because it disregards part of the thing.
That's right.
It disregards back reaction.
That's right. That's right.
So,
But here's the thing, right?
so
It's an effective model that assumes nothing about the existence of a quantum set. So in the sense of quantization of the field, as in like I don't have a quantization map for field degrees of freedom, and yet predicts entanglement in the experiment. That would be my claim. My only claim is that I can present a model that predicts the same as the model where the field is quantized, but yet makes no assumptions about the phase space of the quantum field. As in that quantum field space is quantized. So I'm not claiming. Yeah, it's about the meaning of the words, I guess. What I'm claiming is that you can certainly find entanglement and not need, and work with something like a J-coupling, not need at all a quantum field theoretical description for the field to predict that entanglement.
would you agree that if the experiment was done, and it turned out that the sequence of future experiments would disconfirm quantum field theory and confirm that approximation, that would be an astonishing,
I agree.
much bigger result.
Oh, yeah, totally.
Okay.
Yeah. But not finding entanglement or finding accordance with the other would be huge.
So what you're saying is that this theory either proves that the gravitational field is quantized, or that there's no dynamical gravity at all, and there's no back reaction.
No. You see, that's not what I'm saying. What I'm saying is that the experiment does not disprove some models that make no assumptions.
But this is always true. This is the general point of philosophy of science. Always give an experiment. You can make some model that works only for that particular model, and that is not what you want to do. You just make all the. So
I think that's a compelling model in the sense that I think that if you can falsify this model, then I think there's very little, because this model, the core of this model, what this model has, is not like a random model that we put together like that. What that model has is that this model is relativistically local, while not quantum local. That is the key point of that model. So in the sense, falsifying a model, and I haven't proved this, but I don't think there's any other way to create a model that's relativistically local but not quantum local than this, using the retarded potential formulation for this. Now you can complement it with a stochastic background that is compatible with it. If you want predictions at every time, I didn't give you that. This is skeptical about it, but agnostic, let's say. I could complement the theory with some stochastic model, and then that would be a specific model. I didn't say that. All that this model assumes is that you have a notion of relativistic locality in the interaction that comes from the classical theory, that notion. So I think disproving, getting the experimental regimes with this model or family of models, if you want, because again, you can complement the internal dynamics in many ways. That disproves that model would be big, yeah. I would say. I would say that that way the argument disappears completely. That would be my approach to this. Again, I think it's a compelling argument. Maybe I don't know. I mean, I think that it's compelling that if you quantize the field, let me add two scales of quantity. Let me add h bar 1 and h bar 2. Because let me, for a second, give an h bar 1 for matter and an h bar 2 for the field. And I do two separate quantization processes. One for the field, one for matter. If I make h2 go to 0, if I make the Planck constant in the sector of the field go to 0, I recover the model I gave at the beginning. So, while it's true that it's not a model that I would say is the right model, I don't believe that that model is good. It is certainly a model
Why
that
you don't believe so?
the one that I proposed, that
Yeah, why you don't believe so?
because I do believe that gravity has local quantum degrees of freedom. Yeah.
But why do you? What motivates you to do so?
Electromagnetism, what we know about things, the belief that the universe has to be quantum, at least, or is more plausible that the universe is quantum, that quantum field theory should be able to explain everything, together with the incompatibility of quantum and classical coupling. That's together, to me, more favorable to a quantum theory. But I would say that disproving theories that are relativistically local, but quantum non-local, by an experiment would be big. It wouldn't be small, in my opinion. That would be, I think, the main ingredient of that. And again, I'm not saying also that this model is the model that I believe in, the quantum control one. I'm not saying that the experiment proves nothing quantum about gravity. It proves a lot of things, even in those regimes, in my opinion, it proves a lot of things about gravity, about the quantum behavior of gravity. But I would say that it's still agnostic from the point of view of what the experiment is falsifying. Is not falsifying models that, while still being relativistically local, don't have assumptions on the existence of quantum degrees of freedom of gravity. That's as much as I would think.
There is an assumption about the field. The existence of the field or not?
Assumption about the
Well,
field.
there is a field or not?
There's no quantum degrees of freedom for the field.
But
There is a field, I would say. There is a field, but it's a contact in what sense? In the sense that the field is not dynamic.
Can I measure here? Can I measure field?
Yeah, you can measure a field with this one. Yes.
And the results not massive. So it's,
Well, if you measure, you're gonna get a number. But yeah, you can put it on superposition of the degrees of freedom of matter. That's what you, yes, you can. Yeah.
Okay, I'm gonna stop this here and we'll circle back. There's time, Emma?
Yeah, thank you. So I wonder if you could explain in a little bit more detail what you meant by saying that the quantum controlled model is event local. Because I mean, naively, I would have thought that in order to say that, you're going to have to specify a dynamics for the field so you can tell how effects propagate through it, right? You know, if it gets up into the
100%.
updated, it won't be local. So was there a dynamics, like, was there some story there that I missed?
So the story is that by measuring mass, there's a lot of qualification. You're right in this statement, because I didn't complement it with intermediate dynamics. So you can fit a plethora of dynamics. Some of them would be event local. In fact, if you're interested about a particular sector in the dynamics, you may not be able to find any that is event local. And that's the point. You can find regimes where you can disprove this model 100%. But in particular, if you only measure here and there, then you can guarantee that the action on two only depend on one a finite time. So there's not FTL signaling between the path at the end, at the beginning. So for example, if I make this become an earlier, so for example, I recombine them earlier, this would not be able to tell the difference if it's outside of the line. So for this particular setup, it is event local, but the dynamics, of course, is not event local, because I didn't give you dynamics to begin with.
So how are you imagining the field getting updated?
Well, I mean, I didn't have to for this, but if I had to, I can give you stochastic field theory for gravity. And a stochastic field theory is compatible with the level of the predictions that I gave. I can build one, for sure. It would not be event local throughout the whole trajectory. That is very important. And that's what I'm claiming, that there are regimes. In fact, that's what Wald and Flaminio Giacomini, and I think Esteban Castro, but I'm not sure, did. Well, Alessio Valencia too, I forgot. Oh, Alessio. They actually look at one-way signaling, like times I put them in terms, before these guys have time to actually communicate in both sides. In those cases, you may know, they give a really compelling argument that there would be no event local way. I didn't make assumptions what happened in between.
Brilliant.
Better than everything else. It's interesting how you put it. I mean, you describe this as ruling out semi-classical gravity. In what sense wasn't that already ruled out by the Page-Gallagher experiment?
By what, sorry?
By the Page-Gallagher experiment.
I guess it's ruled out as well by that, but in the sense that you need a full relativistic, you need to combine something that has a full relativistic description, in my opinion, in order to rule it out, no? I would say.
I don't know. Okay. Well, that was what I expected to answer, so maybe I'm not communicating quite right.
Okay.
So here's what I would have thought.
Yeah.
Page-Gallagher is incompatible with pure semi-classical gravity. It is compatible with microscopic semi-classical gravity plus some kind of wave function maps at macroscopic.
I see what you mean.
Whereas that theory is also ruled out here.
Okay. No, yeah, for sure. This is ruled out here. There's no external mechanism of ecoherence or collapse whatsoever. Yeah. So unitary evolution in one case, and unitary evolution tracing out the field in the other case. Yeah, sorry. I misunderstood.
Yes, that's fine. One of the things that I was thinking about as far as
I can't really hear you.
Could you speak up a little bit?
one of the things that I was thinking about as far as with those the Wheeler-DeWitt equation doesn't have time as a variable, and so in this is gravity an emergent property of time, and time and gravity are co-characteristics of the current manifestation of the universe in which we live. Would that be
Okay. So there's some reason why I picked linearized gravity for this. So I have a very nice Minkowski background that gives me a space-time that I can work with in terms of time and space. I would agree, whenever we solve whatever gravity is, I would agree that time, my opinion is along those lines as well. And we're relational, it's not relational, Carlos said it. So the time and space would emerge as, interactions and manifestations that emerge from interactions. I would agree with that. But we don't have that, right? And I never got into any of this, right? I did a full QFT. What I'm doing is QFT, is not quantum gravity, if you want. And I'm doing I'm quantizing a perturbation of the matrix to explain the experiment. However, if you find a regime, that said, if you find a regime where you really need to quantize the linear perturbation in order to explain the result of an experiment, and there's no other way within the hypothesis that we formulated, I think that's a controversial proof that at least a quantum model works for gravity, where a classical or not, something that is not quantum would not work.
So, on the slide where you compare the two models, like with the density matrices, so if I understood you correctly, you're making two arguments. So first of all, you're saying the experiment will not be able to distinguish between the two, and that's basically gives your main argument that the experiment doesn't prove that there are local degrees of freedom for the gravitational field. But then you make an extra argument by saying that the kind of joint prediction that the experiment is only able to measure is obtained by taking the H2 goes to zero limit in both. And I'm not quite sure that first of all, I'm on that important slide of yours, I'm not quite sure that I fully see like the argument for delta not going to zero and for E going to zero indeed. But more importantly, what exactly is added to the we're not proving there are no local degrees of freedom for gravity argument by making this additional and the predictions coincide with the H2 goes to zero.
All right, it's a bit very perfect. So first the technical part and then the observational. So the technical part, this thing is proportional to H bar. This thing, when you quantize the free field, imagine that I give you quantum field, like classical field, and I want to quantize. That's what I do with a linear coupling theory. Like I'm doing weak coupling, so I can separate the sectors of the field from the sectors of matter.
Right.
In general, in GR, you will not be able to. That's why we don't know how to do anything. But
I wouldn't be able to have H1 and H2.
no, indeed, I agree, 100%. You wouldn't. But because I'm doing with gravity,
Right.
in principle, I think, well, I'm going to use the quantization. Well, same as with electromagnetism, right? It's only recently that people are looking at the quantization of the Coulombic part of it, because it's tough, even in electromagnetism. Here was in electromagnetism in QED. In QED, what we do is, okay, we have some Coulombic part. I don't care. We have perturbation over that. And that perturbation is time, space-time dependent. We quantize that. and then we coupling weakly something to it. What we are doing here is similar. Let's quantize the field. So this is, I agree with you, it's not needed for the argument. It's kind of a parallel view that I think helps, or in my opinion it helps, more physics intuitive, I think, in my opinion, but again, that's an opinion thing. Is it following? Let me quantize the free field. When I quantize the free field, there are clearly some parts of the classical theory that are embedded in the quantum theory, obviously, because in some regimes, the quantum theory has to predict the same as the classical one. So what is that survives? What is classical within the quantum theory? Where is the sector of classical physics predictions live? I say, well, yeah, make h bar equal to 0, and you will get what is left. That's what you get. When you make h bar equal to 0, you get with this. And this is the radiation ring function. This is what you will get in the classical theory, propagating the current of particle 1 to the current of particle 2.
Right.
That's the first. So the second, I guess. The second part was...
What that adds to the argument about.
Yeah, from the physics point of view, it's kind of one thing that convinced me a lot. Meaning, like, if I make h bar go to 0, and I can predict it for the sector of the field, and I can still predict the same result of the experiment, I'm not sure I'm seeing anything quantum about it, or I'm seeing much quantum about it. That would be the argument, if you want to.
So this is an argument for saying why not observing the existence of local degrees of freedom should in some sense